Okay, it's right on Western Standard Time, as we said. Could everyone please mute their microphones? That will help. And today we've got a presentation from Steve Barnes, mineral systems in particular, focusing on the Nova-Bollinger deposits in Western Australia that will be of interest to many of you. And this webinar is going to be recorded, so it's available for all participants to view later. There's also an option to ask questions at the end, and if you see there's a little chat option on the side, probably on the right-hand side of the screen. If you type in your questions there, we'll make sure that Steve can come back to them at the end of the presentation and hopefully answer as many questions as possible. We think this presentation will go for about 30 minutes, and after that, there'll be about 10 minutes or so for questions. We hope this will be a good opportunity for CSIRO to promote its research and have a couple of these, maybe one every 2 weeks.
Oh my God.
We're out there in the environment and out, get out into the field. So without any further ado, I'll pass it up to Steve Barnes, research scientist, to presentation.
Ryan, can you hear me?
Yes, I can.
Yes, hi. Can you ask everybody to mute? There's a lot of feedback.
Yes, I'm about to mute all microphones.
Oh, okay, sorry.
I just can't do that with the screen when it's the PowerPoint presentation is showing.
Okay, thanks, Ryan.
Okay, now if Steve's... Can you hear and possibly share your screen in the presentation? And you'll need to unmute, Steve. There you go. I can do that.
Unmute. Can you unmute me? I've lost. No, I can't do that now. I've got the screen up. Hold on.
I have unmuted you. You're set.
Okay. Good. All right. Wonderful. Now I've just got to get my screen back sharing. All right. With any luck, now everybody should be able to see my screen. Are we okay? You got it there, Ryan?
It's coming through now.
It's coming through now. Okay. Great. All right. Well, this is a new experience for all of us, so we'll see how we go. I'll kick straight in. If anything drastic seems to be going wrong, please. We'll start off. So what I want to try and do in the next sort of half hour or so is give you a talk, which is kind of in 2 parts. The first bit is an approach to looking at mineral systems by thinking about them in terms of multiple length and time scales. So I'll take you through that fairly quickly, and then I'll attempt to show how we can actually apply that to an actual sort of point study talking about Nova. So without any further ado, let's jump in. Right, so I'll start out. This is a diagram which anybody who's heard me talk about nickel deposits before has probably seen.
Steve, your screen isn't sharing at the moment.
Sorry?
Your screen does not seem to be sharing.
Okay, it should be. All right, let me have a look. Why is that not happening? Let me try again. How's that?
It's
got it now?
got it.
Good, great. Okay. So starting out with this sort of fairly sort of simple-minded kind of helicopter view of a nickel sulfide mineral system. Magma is generated in the mantle, traversing crustal sill dike networks and producing ore deposits. I'm not going to say really anything very much about this at this stage, except just to point out the one aspect of this diagram which I normally completely gloss over, which is this one down in the left-hand corner, and that's a matter of scale. So scale is what I really want to talk about for the next half hour or so, and not just spatial scales, and not just the sort of kind of 2D view that we're really kind of used to in these sorts of diagrams, but 4D. So I want to talk about how we think about length scales and time scales in these kinds of complicated physical processes. And I'd like to start with an analogy. This is a beautiful picture of a big storm cell, thunderstorm somewhere in the American Midwest. These things make quite nice analogies to mineral systems, because essentially what they are big hundreds of 1,000 kilometer scale weather systems, which are basically hoovering up huge amounts of mass, momentum, and heat at a continental scale, and essentially funneling it all into one place, which is kind of a nice sort of analogy for what mineral systems do for ore deposits. The real message of this is that if the way a physicist, fluid dynamicist, or a meteorologist looks at these kinds of systems to understand them is by looking at them at a whole range of different scales. So what we're actually dealing with here is a whole raft of multi-scale processes, which range from fast processes happening at small scales, like, for example, the condensation of raindrops, which is actually the major kind of thermal driver for what actually makes these systems work in the first place. Sort of medium scale processes, like, say, the formation of cumulus clouds. And then the big scale processes, the big sort of continental context, which in this case would be big sort of kind of global atmospheric weather systems. But the thing that links all of these is that all of these processes feed into one another. And at one end, we have fast intermittent processes operating at small scales. And the aggregation of those turns into big, slow, continuous processes operating at large scales. What I want to show you is how that kind of process, how that kind of thinking can help us illuminate understanding of ore deposits. To do that, I'm going to use this diagram. And this was a plot which was first shown to me by a former postdoc of mine, Jesse Robertson, who's a fluid physicist. These kinds of diagrams are sort of very widely used amongst people who think about these kinds of things. What we've got here is a length scale, time scale plot. We've got time on the horizontal axis with about, I think, 18 log units, something like that, going from milliseconds to the age of the Earth. And on the left-hand axis, we've got length going from nanometers to the radius of the Earth. So basically, absolutely anything on the planet can be plotted somewhere on this diagram. And we can see how they interact all at once. And so what I've got here is a plot which is done for sort of global weather systems. And we can put some of the examples that I showed you from our storm cell. So we can understand how they relate to one another. And one of the things you see on this diagram is that actually a lot of these processes kind of line up in a sort of linear array. And it turns out that linear array, the slope and position of that array is determined by the one sort of unifying kind of physical resistance to all of these processes, which is basically the viscosity of the atmosphere. So that's a really kind of intriguing thing, that all of these multi-scale processes can actually be unified by kind of one essential variable. So let's see how that works in magmatic systems. So here we are back at our magmatic Ni-Cu-PGE mineral system, and now let's try and do the same thing. Now, one of the things that really helps to construct these kinds of diagrams is to understand what the sort of fundamental physical controls are. And in geological systems, particularly magmatic systems, there's really three of them. There's magma flow. So the flow of magma is essentially controlled by the viscosity of the magma. That's the main variable. And so magma flow velocities form a sort of linear array which sits up in the top left-hand corner, sort of the fast end of the diagram here. Then we've got thermal diffusion processes. These are things which govern how fast magmas lose heat to the country rock, and that then flows on into a whole lot of other processes. And then also chemical diffusion processes, and these govern things like how crystals grow in magmas and how sulfide liquid droplets interact with magmas. We know we can actually show where these things should sit on this diagram by a very, very simple rule. And this is a fundamental scaling rule, which says that the length scale of any sort of diffusive process is related to the time scale, the square root of the time scale, times whatever diffusivity happens to be controlling it. So whether it be thermal, chemical, or whatever. So just armed with that one simple equation, we can actually go a really long way. So here's now this is a ferociously complicated diagram, and I'll be breaking some of this down as we go along. But what I just want to show here is where some of the sort of fundamental geological processes that are relevant to magmatic systems sit on this diagram. And the thing in common with all of the ones I'm going to show you is these are things where we can actually observe them, and we actually know the timescales that they happen at. So, for example, lava flow. This is lava flowing out of the end of a lava tube on Kilauea. So typical sort of flow velocities for basaltic magmas are sort of the order of around about a tenth of a meter per second, give or take an order of magnitude or so. And that's what defines this kind of blue field here. The sort of eruption scale for individual volcanic events, so large lava flows, typically sort of months to years, and tens or maybe even hundreds of kilometers. Processes in lava tubes. This is really important for us because we know that lava tubes can erode the rocks that they flow over, and that erosion of country rocks by flowing magmas is one of the key factors in ore deposits. We actually know how fast that happens. It's been observed. That's the order of sort of centimeters and meters in hours to days. So if we extend that out for longer periods of time, tens of meters over years. Large scale sort of volcanic switching events, and I'll explain what I mean by those later. This is the summit crater, a thermal image of the summit crater of Kilauea a few years ago. Well, basically moving around large sort of swimming pools full of magma on a time scale of days. And then going up to bigger scales, so the time scale for individual shield volcanoes is about the same as the time scale for large layered mafic intrusions. Those are forming in sort of hundreds of thousands of years to millions of years, and length scales of sort of hundreds of kilometers. And then finally, the biggest thing we ever really deal with in this game, these are large igneous provinces. That's the Siberian flood basalt province, 3,000 kilometers across. And we know that pretty much all of the action happened within about 2 million years. So that gives you an idea. But now we could, and on top of that, we can now start to think about some of the smaller scale component processes that feed into all of that. So that takes us now to a sort of simple model for how we think magmatic sulfide deposits form. Essentially, magma flowing through some kind of conduit. That magma is interacting with its wall rocks, and it's incorporating sulfur out of the wall rocks by a variety of possible mechanisms. That's making sulfide liquid. That sulfide liquid now has to react with the magma and scavenge the metals out of the magma. They've got to somehow or other accumulate that sulfide liquid into some sort of depositional site by some mechanism or other, separate it from the magma and form the deposit. And that's where we used to think the story ended, but actually what we now know from some work we've been doing in the last few years, it doesn't end there. Sulfide liquids are actually quite mobile and on fairly substantial scale. We're going to be seeing a lot more of Nova. But there's an unmuted microphone somewhere. If somebody could maybe get. Thanks. Okay, so the fundamental question for explorationists, if you want to design an exploration program based around this sort of concept, what sort of length scales are involved here? So how far away is our deposition site from our sulfide incorporation site? That's a really fundamental question if you're designing an exploration program. But to understand that, we also need to understand, as I'll show you in the next few minutes, we also need to know what the timescales are for these processes. Having a look at that. So let's look at the first one. We'll look at how we actually incorporate sulfur into magmas. And there's actually an interesting timescale argument about this, which I won't go into in detail, but I'll just sort of jump to the first conclusion, which is that the main way of getting sulfur into magma is by actually physically incorporating lumps of sulfide-bearing wall rock, dropping them into the magma and melting them. I'm going to have to ask you to take my word for that, but I can give you some justification later. So what happens when we do that? Well, the actual process is quite complicated, and it involves build-up of thermal and compositional boundary layers around the melting zenith. Those might get disrupted by advection and flow of the magma. Turbulent magmas will break those boundary layers down, so melting will be much faster. And when we release the sulfide, that sulfide has now got to grab metals out of the magma. In the process of doing that, it generates compositional boundary layers around the droplet, and material has to diffuse across that. So built into all of this are a whole lot of processes which are controlled by thermal diffusion, chemical diffusion, and actual physical movement of the magma. Solving all of that is actually not simple, but it has been addressed very systematically by Ross Kerr at ANU a few years ago. The conclusion he came to, without dwelling on the details, is that melting of xenoliths typically happens for centimetre to 10 centimetre size xenoliths happens on a time scale of hours to days. And that's going to vary a lot, but that's essentially a good sort of starting point. Now, what we also need to know is how fast are our xenoliths actually going to sink out of the magma? It turns out that's a much more difficult thing to get a handle on because it depends entirely on what those xenoliths are made of. So some kind of xenoliths will actually float in the magma and not sink at all, whereas some will be relatively dense and will sink like stones, literally. So it can be sort of anywhere in that kind of yellow field. But the important thing is that both of those fields sit well below the field for magma flow. So what does that mean? Well, what that means is that xenoliths and any sulfide they have in them can be transported a long way by flowing magma before they actually melt. And the significant conclusion of that is that sulfide liquid transport in magmas might not be as dispersed reactive droplets, as we always thought, but it might actually be within disaggregating xenoliths. And that's a bit of a game changer in terms of understanding how we think about these things. But it also means it gives us an important clue. It gives us an important footprint to look for, because the presence of disaggregating xenoliths in a magma is a really important signal for this kind of process. And it might go a long way to explaining why very often when we look at ore bodies, this is a disseminated sulfide from the giant Rust deposits, we very often find this association between sulfides and these so-called taxitic rocks. And these are basically extremely heterogeneous rocks full of partially disaggregated and partially molten xenoliths. Okay, so that's one part of it. Let's move on to another part of it now, and that's this this stage here of the sulfide droplets actually mixing with the magma and scavenging the metals. How long does that process take? Well, it turns out the time scale for these processes are actually surprisingly long. The reason for that is that the diffusivity of sulfur in magma is actually quite low. So one of the major controls on this process is actual chemical diffusivity, which means that these processes sit on that green chemical diffusivity line that I showed you earlier. And the important thing again is that the time scale for these kinds of processes to happen is relatively long compared to the time scales for significant displacement and flow of the magma. So the conclusion of that is that sulfides can actually be carried quite a long way in a magma before they dissolve. What does that mean? Well, it means that sulfides can be carried a long way in sulfide undersaturated magma. And that's a bit of a game changer, because we've always, one of the sort of basic principles, basic sort of foundations of the paradigm for many years has been that you need sulfide saturated magmas to make ore deposits. Well, in actual fact, maybe you don't. That the initial stage, the fundamental process of actually getting molten sulfide into the magma, might actually happen with most of the magma, in fact, not actually seeing the sulfide, not actually reacting with it. And that could go a long way to explaining some of the sort of the enigmas that when we try to see the signature of sulfide saturation in ore forming magmas. So but essentially the message is that chemical equilibration is really slow compared to transport and settling rates. So sulfides could be carried a long way from their source in magmas. So what does that mean? Well, it means that to actually make an ore deposit, or if we want to think about the way ore deposits are being made, we don't want to be thinking at that time scale. We actually need to be thinking at larger and longer length scales and longer time scales, and perhaps more along the lines of the sort of time scales for forming individual large lava flows or individual Hawaiian type flow fields. And that's more along the lines of sort of tens of kilometers and hundreds to thousands of years. So let's now start thinking about this sort of scale, where we're looking at a crustal magma network at sort of 10-kilometer kind of scales. Here's another complicated diagram. Don't worry, I'm not going to dwell on this in detail. This is just to sort of illustrate a principle. If you want to read more about this, this was in a paper we wrote in Ore Geology Reviews in 2016. But the point of this paper was that ore forming systems don't sort of form just at one place in the crust. They're part of large systems which actually transect the crust. One of the fundamental drivers for forming ore bodies might actually be the gravitational potential energy which exists in these kinds of systems, where you've got sill and dike systems developing over perhaps tens of kilometers of crustal thickness. Sulfides might be forming at different places. Sulfides might be accumulating at certain stagnation points and then getting remobilized. The key thing is to make an ore deposit, we actually need to keep these systems open and operating on big enough length scales, but also on long enough time scales of sort of thousands of years or so. So we need long-lived, continuously operating magmatic systems. The other point about this is that magma in these kinds of systems doesn't necessarily only flow upward. In fact, we know from studies of radial dikes and other big sort of crustal scale magmatic systems, a lot of magma transport in the crust is not so much vertical as lateral. And we also know from some evidence that I'm about to show you that magmas don't necessarily only flow up, they can also flow down. And here's a fine example of that. This is at the top left there, that's a picture of the summit crater of Kilauea, so-called Halima'u crater. That's as it was in early 2018, which is the last time I was there. And what we've got there is a pit crater, a caldera. It's about a football field in size. It's about sort of at the MCG across, and it's full of molten lava with a nice black crust on it. That's what it looked like then. A few days later, that lava lake had completely drained, and a few months later, it looked like what you see on the bottom right of that slide, and that is a completely collapsed, essentially new caldera, which is more than 10 times the size of the original one. And what that represents is a gigantic withdrawal and collapse of the underlying magma reservoir. And the amount of magma that was drawn out of it, interestingly, is about the same sort of volume as the volume of a typical small intrusion that hosts nickel sulfide deposit, like, for example, the Nova intrusion that I'm going to show you shortly. Okay, so what caused it? Well, what caused that was that a different part of the plumbing system opened up, magma drained out of the summit reservoir and flowed off down to the east end of the rift and produced these spectacular huge lava flows, which everybody was watching on their TVs a couple of years ago. Almost sort of wiped out a couple of small towns in Hawaii. But that process, sort of 30 kilometers away, culminated in the collapse of the summit caldera. So that kind of got us thinking, well, maybe that sort of magma withdrawal and drawback process might actually be what controls the formation of sulfide ore deposits. So this is sort of the culmination of the sort of sequence I showed you earlier. We're generating sulfide accumulations at different levels within a vertical conduit system. Then we drain everything out, everything drains back, the sulfides then accumulate in choke points within that network. And that actually explains a lot of the features that we see in a whole variety of different deposits, particularly deposits hosted by small mafic intrusions. So that then goes a little further to thinking about sort of analogies in the fluid dynamic world. This particular analogy was suggested to me a few years ago by my old friend and colleague Reed Keyes. And this is the notion of an ulutriation column. Ulutriation is an industrial process which is used for separating solids from slurries. And the way it works is you have some sort of a vertical pipe up which you pump a suspension. So this is a fluid with particles in it. So in this case, this is magma with sulfide droplets in it. And if you can adjust it in such a way that the particles are settling at the same rate as the upward flow, then you can produce a nice kind of segregation of your particles from your fluid. But if you keep this flow going at faster than that rate, then what you can do is essentially keep those particles suspended for a long period of time. So essentially, the ore-forming systems, I would see them as being basically large crustal scale ulutriation columns, where for most of the life of the system, you're actually pumping magma through it, entraining sulfide, or perhaps keeping it in temporary reservoirs, but continually reacting it and enriching it. And it's only at the very end, the very last stage, the caldera collapse stage, when everything drains back, that you actually form the ore deposit. And of course, that's the last thing that happens, and that's the last thing that you see. So coming back to our length scale, time scale story, just summarizing some of the major conclusions for that. Magma flow is the fastest of all the essential processes. Rate of melting of Zenith is a really important control on how you actually make the sulfide liquid. Sulfide liquid might be transported largely within melting xenoliths. Once you do make sulfide droplets, they tend to settle or segregate much faster than they can actually react with the magma. So putting all of that together, ore formation requires multi-stage recycling, long-lived transcrustal conduit systems. Now, if you want to read about that in a bit more detail, that little QR code in the top right-hand corner there is a link to the paper that Jess Robertson and I wrote in Geoscience Frontiers a couple of years ago. And that's an open access paper, so you can download that and have a read of it. All right, so that's sort of the first bit. Now we'll move on to the bit that probably most of you are really interested in, which is the Nova-Bollinger ore system. So we'll take you there. Here we are in the Albany-Fraser Orogen, down in the bottom right-hand corner of the Yilgarn Craton. We're sitting in a Proterozoic origin, the Fraser zone, rocks mostly around about 1,300 to 1,400 million years old. There's Nova sitting in the middle of this big body, which is kind of green on all the maps, but in fact it's not entirely green. It's actually a mixture of metasedimentary, what look like continental margin sediments, very, very heavily intruded by a huge volume of mafic sills, one of which is the Nova body. Here's the local geology of Nova. That's the blue features there are iron-rich metasediments, which define the famous eye. And the red thing there is the surface trace of the Nova-Bollinger ore body. I will take a look at a long section through the Nova system, looking to the north. And here we have the upper intrusion is a layered intrusion, thick layered intrusion, about 500 meters or so thick and several kilometers across, interlayered peridotites and norites, with a lower marginal zone of pyroxenitic and noritic rocks with relatively little sulfide in it. A little bit towards the base, not much in the main layered sequence. And then sitting underneath that is the lower intrusion, which is essentially the host to pretty much all of the ore bodies. So now if we have a look in 3D, this is now from IGO's leapfrog image from the Nova-Bollinger mine. And at this point, I'd like to thank IGO for permission to firstly for funding the project, and also for permission to show you this material. So that's now looking down on top of the lower intrusion with the upper intrusion removed. And what you see is this sort of elongate, that sort of green blob is an elongate, basically tube-shaped intrusion with lots of sort of lots of kind of smaller finger-like projections off the left-hand end. So now we're going to look along that. So that's our view now, looking along the axis of this intrusion. And that's what it looks like. And see in cross-section, it's a sort of lozenge-shaped kind of a body. This is a classic example of what we call a chonolith. It's an elongate tube-shaped intrusion. It's about as thick as it is wide, but it's much longer than both those dimensions. The green is the, I'll show you what that's made of in a second. The red and orange are the ore bodies. And as you can see, a large proportion of the ore bodies actually sit in the country rock, not in the intrusion itself. This is what a lot of the intrusion's made of. I'll show you a few of these kinds of images, so I'll just spend a second explaining it. This is an XRF element map. This is done on a desktop XRF mapper. So where you essentially take a piece of drill core and raster it under an X-ray beam and measure the concentrations of elements. For this particular map, I've combined three elements, chromium, iron, and calcium. And that works particularly nicely for these rocks. It brings up the olivine in a sort of darkish green color, brings up orthopyroxene in these sort of greeny browny colors. Sulfide is the bright green, and clinopyroxene is the sort of bluey pinky colors. And the reason you're seeing different colors within different phases is because the pyroxenes are actually zoned. And we'll get onto that in a second. But this is a really distinctive and characteristic kind of texture. What we've got are basically these sort of cauliflower-like clumps of orthopyroxene sitting in a matrix, in a sort of open framework of olivine. So this is essentially an olivine orthopyroxene cumulate, but it's a very distinctive texture, a very unusual looking rock type. Here's a couple of other images of it. That's the XRF map at the top, and then the phase diagram at the bottom. Sorry, the phase image at the bottom. I've translated those colors into the actual minerals. And then there on the right-hand side, there is a blow-up of part of that map. The green and orange things that you can see there on the right-hand side, those are orthopyroxene grains. And those complicated patterns that you can see in the middle of them are patterns due to variation in the chromium content. And they're actually reflecting a variety of different types of zoning in the pyroxene grains. And what that's telling you is that these pyroxene crystals actually grew really fast. The implications of that are pretty interesting, because as we'll see, I'll show you that a lot of other aspects of Nova seem to follow from the fact that it cooled extremely slowly. So how do we reconcile those kinds of things? Here's another example of that sort of zoning process. This is actually a synchrotron XRF map. And again, the green and orange things are orthopyroxenes, and that sort of bow type feature you can see there is sector zoning, which is a characteristic marker of disequilibrium, rapid growth of pyroxene crystals. The other things these rocks have in them are what we call symplectites. This is another XRF map from the Australian synchrotron. This is chromium, iron, and titanium you can see there. And these complicated sort of wormy things you're seeing there are the result of a reaction between olivine and plagioclase. You put olivine and plagioclase together in these rocks, they don't like one another and they back react to form these complicated assemblages of what are primarily amphibole and spinel. These things are arguably high temperature metamorphic to very, very late stage igneous processes. We think we can make a case that these things actually start to form while there's still actually some melt in the rock. And on the basis of that, we can use the pressures and temperatures that we get out of them to tell us the emplacement conditions. And that tells us that these magmas finish their solidification at around about 0.8 to 0.9 gigapascals. That's 8 to 9 kilobars in the old money, or around about 25 to 30 kilometers depth. So these magmas are emplaced deep in the crust, in the lower crust. That's a very, very significant conclusion. And the evidence, and that's not the only line of evidence. The other evidence is that we have very high aluminium pyroxenes in these rocks. They have spinel solution in them. That can only happen at high pressure. The spinels in the rocks are not chromites. They're low chromium, aluminium-rich magmatic magnesian hersonites. And again, those things only form at high pressure. And then, as I'm about to show you, the sulfide textures give us an important clue as well. But what's important is that the temperatures that pressures and temperatures that we get out of these indicators are basically contiguous with the regional metamorphic grade. So these intrusions were emplaced into granulite facies rocks at about 30 kilometers depth at around about 850 degrees C, which is what the regional metamorphic assemblages tell us, according to some excellent work that's been done at Curtin. Okay, so that's emplacement conditions. Now let's have a look at the sulfides. This is a very schematic image. This is not sort of a real map. This is just a sort of cartoon simplification to show you the relationships. But what you have there in purple are the ultramafic rocks of the lower intrusion, and then the sort of dotty stuff underneath. These are the net textured and disseminated ores within the lower intrusion. The yellow and green stuff are the country rocks. These are garnet-bearing paranysers and mafic granulites. And the orange stuff is the sulfide. So what we have in the country rocks here is a whole series of different textures showing sulfide invading the country rock in different ways, forming a variety of breccias, intersecting vein arrays, sulfide veins, and soft and hard wall breccias, and sulfide infiltration textures. I'm not going to go through all of these, but what I want to focus on are the two down in the bottom left there, the soft wall breccias and the infiltration textures. And this is what they look like. This is a beautiful, spectacular underground face, of which we see lots and lots at Nova, the most spectacular ore body I've ever seen anywhere underground. And the upper part of that image on the left is basically a matrix of sulfide with rafts of disaggregating fragments of metapelitic gneisses. So these are basically garnets, quartz, plagioclase, pyroxene rocks, which are disaggregating to various degrees into the sulfide. And then down in the lower part, you're seeing a vein of sulfide, which is actually cutting into the gneisses. And off the walls of the veins, you can see the sulfide actually infiltrating along the foliation of the gneisses. Here's another one of these interfaces close up. We've got sulfide with nice fragments at the top. At the bottom, we've got nice with sulfide interface with sulfide veins and sulfide infiltration features. Garnet bands there showing up in the sort of pinkish colors. And what we're dealing with here is basically an infiltration melting front where the sulfide is melting its way into the country rocks. Now where we get a high proportion of sulfide, so up at sort of at the top of these, at the top of this zone, then fragments of the country rock actually detach themselves and float off into the sulfide and make things that look like this. This is a photo from Seb Stauder from the early days of the Nova mine. So you're looking at fragments of gneiss sitting in the sulfide, and what's left behind basically are the most refractory layers. So the black material that you can see there, these are the pyroxene plagioclase rich mafic layers, whereas the more sort of pelitic material disaggregates. Here's another one of these XRF maps, and this one is a manganese iron calcium map. The garnet shows up there in the orange colors, and the green colors are sulfide. You can see that the sulfide is basically completely permeating the rock. What you can also see, and I'll show you a little bit more of this in a minute, is that we're actually also seeing magmatic textures within the sulfides. We'll come to that. So here's the process taken a little bit further. This is now sulfide completely permeating the foliation in the gneiss. And this is a close-up of a fragment of that. These are XRF maps. Again, the sulfides are in sort of orangey colors here. Garnet in blue. That's a phase map, so you can see the different phases, and you can see that the more sort of coherent blocks are these kind of pyroxene plagioclase rocks, whereas the garnet-rich material tends to break up and disintegrate, get invaded by the sulfide. And finally, here's what the sulfide looked like. So here we've got the different colors are showing up the sulfide minerals. The greenish color is chalcopyrite, the blue is pyrrhotite, and the pink is pentlandite. And those sort of textures that you're seeing there are what we call loop textures. And these are textures that are formed by the magmatic solidification of the sulfide at around about 850 degrees. In other words, at the temperature indicated by the metamorphic grade in the country rocks. So basically the sulfide in these rocks solidified really slowly, but as we've seen from the zoning in the pyroxenes and the silicates, the initial stage of the solidification of the silicates is actually quite fast. So how do we reconcile those things all together? We'll get to that as a conclusion of the talk. Just one other thing I want to show you. Along the margins of these sulfide infiltration zones, we typically get these bodies of felsic pegmatite. There's one, you can see one there. Here's a really beautiful smoking gun example where we can actually trace one of these things actually out of the gneiss. It's a leucosome layer within a magmatic gneiss, actually draining out into the wall of one of these sulfide veins. So what do we think is going on? Well, basically this is the sulfide, as the intrusion comes in, it's carrying sulfide with it. The initial phase of the injection of the intrusion, I think was actually carrying sulfide at that stage. So rather than it being sort of sulfide that's dropping into a pre-existing container, the sulfide's actually there all along. And in fact, the sulfide might actually be a major agent of actually eroding and replacing the intrusion. But that's a story for another day. But one of the key things is that accompanying this intrusion, the country rocks were actually an extension, and we actually started to generate fractures. The sulfide injects itself into the fractures, and heating up the country rock even further. Remember, the country rock's already pretty much at its melting point before this even starts. So this extra heat carried in by the sulfide pushes it over the top. That generates melting within the less refractory bands of the gneiss. And that melt drains out to form these leucosome patches along the walls of the veins. Meanwhile, in places where you've had really intensive injection of the sulfide, these infiltration melting fronts at the top is where we form these soft wall breccias, where fragments of the gneiss actually become detached and float off into the sulfide. So, so what we're seeing is something that's relatively unusual. The infiltration melting fronts are not uncommon. They're present in lots of different ore deposits. We find them in komatiitic hosted deposits. We find them at Norilsk. We find them lots of other places. But what's unusual about Nova is the lateral extent, and that they extend so far, tens of meters, perhaps even up to 50 meters away from the actual original margins of the host intrusion. So why is it they go so far? Well, this is basically all about the thermal regime that we're sitting in. So we can get a little bit of a handle and actually start to put some numbers on these timescales. By just sort of applying a few sort of simple principles. One of the things we can do first is just to do a very, very simple just heat conduction model for a 100-meter thick sill injected into country rocks at 850 degrees. And that's what the model on the left is. And what that tells you is that to cool the magma in that sill down to close to its solidus temperature, which is the temperature recorded by the symplectites, takes somewhere in the order of about 1,000 years. So it's actually a pretty quick process. But now we've formed our ore body in country rocks which are at 850 degrees. So now they're basically going to sit there, and the time scale for the cooling of those sulfides has got nothing to do with the cooling of the intrusion. It's now all about how long it takes to actually unroof, exhume the origin, and cool that entire mass of deep crustal rock. Now we know from some beautiful work that was done at Curtin by Lyskobiorsky a couple of years ago that roughly what the sort of timescale for that process was. And it turns out that the cooling rate was something of the order of 10 degrees per million years, based on a variety of different thermochronometers which record metamorphic conditions at different times. So, so that lets us construct this sort of timescale diagram. So we've got time on a log scale on the horizontal axis there, temperature on the vertical axis, and we can stretch out the sort of the initial magmatic phase, but then the stage in which the sulfide is cooling and solidifying and percolating through the country rocks is actually happening not over hundreds to thousands of years, but over millions of years. And it's that extended time scale which really lets Nova become the strange beast that it is. Okay, so I'm just putting let's go back to our length and time scale plot, and we're in the home straight now, we're near the end. We can start to put some of these features on the diagram. So here's some of our zone pyroxenes. Now we know that these pyroxenes must have grown faster than components could diffuse in the melt to keep up with them. So that gives us a way of actually plotting this on this diagram. And we think that these things must have been growing on a time scale of a few days. Solidification of the intrusion, I've just shown you, around about sort of 1,000 years or so. Solidification of the sulfide, probably millions of years. Migration of the sulfide, this is a slightly more complicated estimate, but essentially you can model this as a Darcy's law fluid percolation problem. And it turns out that the typical timescales vary depending on which bit of the system we're looking at. If we're looking at sulfide percolating through the actual ultramafic cumulates in the intrusion, that's really fast. That's happening at meter scales and in years. Percolation of sulfide into the gneisses and formation of these leucosome veins and so on, that's a lot slower because that's controlled by viscosity of the silicate melt, which is much, much higher. And that's probably of the order of tens of thousands of years, perhaps hundreds of thousands of years, over tens of meters. But still well within the time that we've got available to us, which is the time scale of the exhumation of the entire origin. So that's basically the time and length scale sort of picture of Nova. And the conclusions are that Nova sulfides are, as we know, extensively developed in the footwall rocks. This is the result of, at least in part, of primary magmatic processes. There is a fair bit of tectonic mobilization as well, but the fundamental control is primary magmatic. Emplacement was syntectonic, syn-metamorphic peak into the country rocks close to the solidus temperatures. Sulfide liquids spent a long time cooling through its melting range, and there was probably sulfide liquid there for millions of years. The distinctive features of Nova are due to this high temperature emplacement, exceptionally prolonged cooling path, and also, I haven't touched on this, but deformation during emplacement. And then, so taking that out and just recapping some of these conclusions that I gave you earlier, but just now again, it's sort of in the context of Nova. You can read that as well as I can. I'll just remind you again, if you want to download that original paper, that's the link there. I will leave you with that. Just with the final thought down on the left there, scaling relationships are really important. Kinetics are really important. Even in what you might think are really slowly cooled, long-lived systems, kinetics are still really important and a major control on all forming systems. And the main thing I'd really like you to take away is this is a really useful way to think about mineral systems, or actually for that matter, any other geological process. So thanks to my collaborators, Jesse Robertson, Valentina Taranovic, Steve Beresford and the IGO Nova Karoo, Louis Schonefeld at CSIRO, and everybody who's helped out and been involved in this work over the last few years. So thank you all for listening.
Thank you, Steve.